our next speaker. Stefano Covino is an enough astronomer currently working at Osservatorio Astronomico di Brera. His research interests are gamma lightning, gamma ray bursts, and high-energy astrophysics in general. He has worked on robotics for telescopes and optical instruments, as well as in many foreign institutions. He is very active in scientific outreach. So please, thank you. And
You're welcome. Okay. Yes, I like it. Very good. Hello, everybody. It's a pleasure for me to be here, of course. And if I succeed, I'm trying to tell you a beautiful story, a story of knowledge, of development, of mistakes, but a story that can show how sometimes the knowledge in astrophysics and in all possible kind of sciences actually can follow random routes, actually. Let's go immediately to the main point. I'm sure that essentially all of you have tried to look at the stars, and in spite of the fact that possibly you are not very confident with the constellations, with the name of the stars or so, you know that there are bright and faint stars, that there can be planets moving slowly or not so slowly, but essentially you are not surprised if you look at the stars. However, if you have the possibility to have a satellite in orbit with a camera able to detect gamma rays or hard X-rays, as we technically say, the sky is completely different. And what you can see is something like this. Look at the time axis. These are seconds. Well, the movie is a little bit accelerated. You don't see absolutely nothing, anything actually, and all of a sudden, in a few tenths of a second, something appears. It becomes extremely bright, thousands of times brighter than the background sky, let's say, and in a couple of minutes, nothing remains. This is a gamma ray burst, something that attracted the attention, the passion of a large fraction of astrophysicists since the last 50 years, actually. So let's go quickly to the beginning of this story. We are in the 60s, when the space age was beginning, and you know that apart from nice things, humanity can do very nasty and unuseful things, like war or other related things, but occasionally some good agreement is signed. In 1963, the three main, possibly for the time the only nuclear powers, signed an agreement, the USA, the USSR, and the UK, well, essentially to avoid to try to make explosions, nuclear explosions, on the ground, under the sea, or in the atmosphere. And just to be sure that everybody was not only signing but respecting the agreement, there was the right to control, to check, to guard what the other countries were doing. The USA, and in a sense we can say the Western countries, sent to orbit a constellation of satellites that were extremely advanced for the time. The satellites, you can see, they were not that big, 1 meter size or so, and these satellites had the capability to detect strong and short in time impulses of gamma rays, because one of the main features of a nuclear explosion was that at the very beginning you could have, for 1 second or a fraction of a second, depending on the specific case, a powerful flash of gamma rays. So these satellites in orbit could control that nobody was really violating the ban, the treaty. There is a curious thing. Of course, they were checking, these satellites were designed to check what was going on Earth. But, as you might remember, or you might know actually, yeah, you are all very young, in the 60s, in the early 60s at least, the Soviet Union was leading the race to the space. And so the Americans were really scared by the possibility that the Soviets could have the technology to send nukes, or nuclear bombs, if you like, to the moon. So these satellites had also the capability to look on the other direction, in the opposite direction, the sky, just to see what was going on. And what happened? Actually, it happened that these satellites basically did not detect nuclear explosions on the ground because more or less the treaty was respected, but detected many gamma ray pulses. This is the first one in July 1967, and very quickly, the scientists related to these missions, they were military missions, but of course there were many scientists working with them, realized that these pulses were not coming from the ground or from the moon, but they were coming from the outer space. At that time, nobody really knew something more. This is Ray Klebezadel, the first scientist that published something about these gamma ray pulses that were called after him gamma ray bursts. And this is a publication happened 6 years after the real discovery. There are many legends about this delay. Some people say it is due to some military secret that was eventually declassified or something like that. According to him, nothing of that is true. They simply needed a lot of time to be sure that they were not observing some atmospheric or strange phenomena not really related to astrophysical sources. And for, let's say, 20, 30 years or something like that, this was essentially everything we knew about these events. And a breakthrough came when, in 1991, a devoted satellite to gamma-ray observations was launched, again a NASA satellite. This is the Compton Gamma-Ray Observatory. Compton is the name of a very famous and clever physicist. And this is a satellite that you cannot really see it, but it's very huge. It was very huge and heavy, and had aboard detectors able to look with an impressive time resolution these events. And this is one of the most beautiful, but not unique at all. It is a gamma ray burst. Look at the time scale again, 1 minute, something like that. You have variability at, with a rhythm that is, let's say, quicker than a millisecond. So you have a huge and wide variation, rock and roll, something like that. And although I don't want to go in details because this is not the right place, if you measuring the time scale of the variability, you can have an idea about the size of the emitting region. This is a very well-known and basic physical rule. What you can get in these specific cases is that the emitting region was at most tens of kilometers big. So quite short, quite small indeed. The size of a black hole, to be specific. And that was considered very intriguing by all the astronomers of that age. What is the problem, actually? You can have wonderful satellites, indeed we had, we still have, with advanced technology, but localizing the emission of gamma rays is a difficult task in a technological and intrinsically in a physical sense. Those instruments were able to say that we are receiving a gamma ray burst from a dead location in the sky with an error of the size of about 4 times the full moon. So a very large error. There are billions, literally, of stars, galaxies, and other astrophysical objects in a region as large. So in spite of that, detecting a lot of these sources, this is a very interesting way to solve a scientific problem. You can hope to find a solution in a statistical way. This is a map at high energies of our own galaxy. And these red points that you can see are pulsars. Pulsars are neutron stars very quickly rotating with the powerful magnetic fields typically, and they are very important sources for many reasons. And you can see that they are distributed in the sky. This map essentially shows you all the visible sky, but most of them are on a plane, and this is the plane of our own galaxy, where most of the stars actually lie. So the idea was rather simple. If we draw the position of many gamma ray bursts that we are detecting with our satellites, if they follow more or less this distribution, we know that the progenitors, the astrophysical objects generating these pulses, are probably part of our own galaxy, as most of the stars that we can see during the night. Otherwise, if they are uniformly distributed in the sky, they are very likely of a cosmological origin, because we know that on a rather large scale, the universe is very homogeneous. There are galaxies everywhere. And this is the result. Compton, in several years of work, detected 2,000 or 3,000 gamma ray bursts, and forget about the colors, but the position are on a map with the same projection of the map that you have just seen, and you can see very quickly, very easily the answer. They are uniformly distributed. So in spite of the fact that we don't know how far is the progenitor of, I don't know, this event or any specific event, we knew that the origin of this gamma ray burst were cosmological. So at very large distances, much larger than our own galaxy. And immediately, the energy that you can compute are associated to this event became impressive. These are very energetic phenomena able to generate energy, let's say, comparable to a supernova, so the huge explosion of a star, of a massive star, but emitted in a few seconds at most. Then the Italians came, because this is actually an Italian story, indeed. You might not know very well, or probably, or possibly you know, but Italy is, or has been, a space power. Italy has been the third country with the capability to launch a satellite in orbit, and there is a long tradition, even here in this institute actually. And in 1996, an Italian-Dutch satellite, where Dutch contributed for, let's say, 10% of the hardware, was launched. This satellite is known as Beppo-SAX. Beppo is the name of Giuseppe Occhialini, a very famous astronomer that worked in Milan too, and actually was one of the fathers of the high-energy astrophysics in Italy. And this satellite had an impressive reliability, was able to solve some of the most important, most difficult scientific problems of the late 90s. And how? Well, apart from a very sophisticated set of instruments that I cannot describe now in detail, this satellite had a capability that might sound trivial if you don't know anything about space technology, but actually is really amazing. SAX was designed to have the capability to repoint automatically, or almost automatically, to a new target in 6-8 hours. And believe me, considering the epoch, 25 years ago, that was really, really impressive. Having the capability to repoint very quickly when you have a gamma ray burst, you could check one of the predictions that the theoreticians to us. One of the predictions was that you have a gamma ray burst, it lasts for 10 seconds or whatever, then you don't see anything at the gamma rays. But if you observe at frequency or lower inner energies, X-rays, optical, maybe radio band, you could see something else, what is known as the afterglow. And actually, Sachs found it, identified the first afterglow. I know that these pictures are not really easy to understand, but you have a source that after a few days disappears or is fading quite quickly. And having the capability to detect the position of this source with much better accuracy, you could also use an optical telescope and identify a tiny point that is actually a cosmological galaxy, a far-away galaxy. A galaxy at about 8 billion light years distance. So that was the first case allowing us to measure, directly measure the distance of a gamma ray burst, and therefore opening, let's say, the era of the quantitative measurements of the qualities of the features of these events, because we could also not only observe what they do, but also know where they are generated, and study the progenitors, and so on, and so on. The next step is close in time, 10 years ago or something like that, when an impressive, really, satellite with impressive technology, as you will see immediately, was launched, and it is a satellite built by 3 national agencies, USA, UK, and Italy again. It is still operational, it is still flying, and this satellite essentially has on board 3 main instruments: a gamma ray telescope, the one that could see the gamma ray burst, then 2 telescopes with the capability to locate very accurately the position of something, an X-ray telescope and an optical telescope. The X-ray telescope, most part of the X-ray telescope has been developed in Italy and specifically in Milano, in the Brera Observatory. And however, SWIFT was not only an advanced technology satellite, but completely changed the way the astronomers do their job. I mean, I'm sure that you might think to an astronomer to thinking that he or she is something working very quietly in a quiet environment. The stars are still there, actually. It's cloudy tonight. Okay, no problem. Tomorrow, or maybe the day after tomorrow, or so or so. Well, maybe that was true in a very far past. But actually, this is no more true. And the SWIFT had the capability to react in a complete automatic way. Sorry, I just want to see again the animation. To any newly detected gamma ray burst. And in a minute or so, not 6 or 8 hours, a minute, the satellite repointed, got data, and transmitted the data to the ground with a network of devoted small-sized satellites. And what happened? Anytime the satellite detects a gamma ray burst, there is a teleconference opening immediately at any hour, day or night or whatever it is, and you see astronomers from Italy, the USA or the UK discuss together about what it is the case to do next, if it is the case to have ground-based observations with big telescopes, or if the event is not that interesting and the satellite could be left to follow a different activity or so. So, in spite of having people completely separated in space and time, you have a generation of astronomers that got the feeling to work together anytime, even if they really work in completely different, geographically speaking, environments. A real revolution in a sociological sense. So actually, since I don't have so much time, what are these gamma ray bursts? Well, gamma ray bursts are very impressive events indeed. We have a phenomena that I will mention in a couple of minutes, injecting a huge amount of energy in a very small volume of the size of 10 kilometers or something like that. If you do that, with some conditions that I'm not describing in detail, you generate an impressive plasma ball expanding at the speed of light. It is called a fireball, actually. And during this expansion, you can have these homogeneities inside, and then these inhomogeneities generated the gamma rays that you are observing. And eventually, when this expansion will begin to collect gas and dust that there are in the space, you are like decelerating this fireball, and this deceleration converts kinetic energy to radiation. And these are the radiations that we receive and we call the afterglow. And how they are produced, we still don't know everything. Actually, we never know everything, of course. But there are good theories, good ideas. There are possibly two different channels to generate these events. One happens when you have a very massive star that can explode as a supernova. We know very well these events. But in a few peculiar cases, and these peculiarities are not clear yet, this supernova is associated to the generation of two very powerful jets. And these jets are exactly where the gamma ray burst is going on. If the Earth is by chance on the direction included in the opening angle of the jet, we, from Earth, detect a gamma ray burst. Another possibility that generates a phenomenon very similar, actually, but it is quite different originally. You can have a couple of compact objects, typically two neutron stars. If they are very close to each other in their orbit, they emit gravitational waves, as we know, because they have been detected 1 year ago, and the orbit shrinks. Eventually, they crash. They coalesce on one and the other, and they generate a very complex. This is a very complex phenomenon, but they very likely will eventually generate a black hole. During this phenomenon, again, jets can be emitted, and again, if Earth is randomly on the direction covered by these jets, we, from Earth, say we are observing a gamma ray burst. So we started with a spy story, with satellites looking for violation of a war treaty, and eventually we got scientific satellites able to move as in science fiction movies, to point automatically. There is a lot of artificial intelligence aboard these machines, and to observe phenomena that are completely different compared to the long and quiet evolution of the stars of the galaxies, billions of years or so. These events happen in a few seconds, a few minutes in the slowest cases, and they really gave the birth to the rock and roll astronomy, the astronomy of a very rapid, violent, sometimes, amazing, frenetic events. And that's it. Thank you a lot.